Our next speaker in the session will be Kevin Young from Sandia National Laboratories, talking about roles for conventional supercomputers in quantum benchmark.
Thanks. Hi, so like I said, I'm Kevin Young. I'm from the Quantum Performance Lab at Sandia National Laboratories. Most of what we do is we spend our time thinking about why quantum computers don't work. And I was coming to give a talk here at NERSC, and so I thought it'd be nice to talk a little bit about how we're using conventional supercomputers in our work to help people understand and improve their quantum devices. The main problem that we're trying to answer with benchmarking research is how can we understand a quantum computer with just a few numbers, right? Quantum computers are these big, very complex, state-of-the-art physics experiments, and we want to describe them as 10 to the minus 4 or something that where we can explain to someone who doesn't necessarily know the intricate details of our device, just 1 or 2 or 10 things that they can use to say, oh, I would like to buy this computer and not that computer. So, we might consider questions like how many qubits does it have? Or how much does it weigh? Or how much does it hurt when I drop it on my toe? All of these things are probably going to be useful in the future, but right now, does it work at all? Is really one of the questions we want to answer, right? So the key point that we're trying to address in benchmarking now is what are the errors that we're experiencing? So we know that the computational power of current devices is limited by the errors in the device. If we had Willow or something, Google's superconducting or quantum computer, and it had no errors, that would be a very, very useful device, right? We could learn a lot with that. But there's errors, so its computational power is severely limited. We're going to have to use error correction. This is a Saturn V rocket, not a quantum computer, but it does, I think, convey one sort of, I think, useful analogy here, which is the entire purpose of the Saturn V rocket was to put 500 pounds of people on the moon, right? And it weighed 6 million pounds. So similarly, quantum error correction, the goal of that is to convey a few hundred or a few thousand logical qubits to the very end and using tens or hundreds of thousands of physical qubits. So, and if we can reduce the errors, then we have the potential for dramatically reducing the amount of overhead that we need to get our quantum computation to the moon. So this is, we saw a picture of a quantum computing stack earlier from Ockel. This is a little bit more cartoonish, but it does display all of the things we might want to benchmark about a quantum computer and how we might go about doing that. So in the blue boxes here, we have one abstraction view of how a quantum computer works. At the very top, you feed in a computational problem. I want to solve this SAT instance, or I want to solve this quantum chemistry problem, or I want to solve this factoring problem. And then each of those problems gets broken down into maybe a set of subproblems. There's quantum algorithms that you may want to consider. Then you have to compile that algorithm for your specific piece of hardware. You may have a compiler that breaks it up into fairly high level operations, which you then need to break into lower level operations. And finally, those get turned into pulses that get applied to your quantum computer. There may be a classical coprocessor, which could be a very large supercomputer in itself, that's processing error correction data as it's coming off, or processing other kinds of mid-circuit measurements, or in the case of VQE, processing data and then turning it into changes to some parameters. And then out comes raw data. Maybe that has to get analyzed. And through all of these different levels, there's software or hardware that itself, all of it could be benchmarked independently in groups. So we could imagine a set of computational problem benchmarks where we just say, here's a problem, tell me how good you are at like getting me the right answer. Or you could say, here's a compiler benchmark. I want to know what is the smallest number of t-states that I can like consume to solve this problem. There are also high-level program benchmarks where I say, I want to run this quantum circuit. I don't want to necessarily solve a problem. It's just a circuit that I've defined, run it. Let's see how well that worked. I could also look at low-level programs where here are some, very like sort of detailed pulse level metrics maybe that I want to run, or pulse schedules that I want to run. And all of these things are useful things to do. They answer certain people's questions about the utility of their devices. Some of them, as you see, like the compiler benchmarks, don't even use the like qubits in the middle. But for the problems that I'm interested in solving, we are interested in understanding why that white box in the middle of all the blue is like failing. So here's an example of a very simplified benchmark. I just pick a problem, run it on the quantum computer, and see if you got the right answer. And in many cases, this is like the entirety of what we're doing, sort of distilled down into 3 steps. But if you pick up the wrong problem, then this benchmarking approach like can have some problems itself. So you may ask, what if I do, I want you to factor a number. Like, here's an RSA integer, please factor this for me. Well, you probably can't run that. Even, small devices that people have now probably can't even factor like 21. We could also be giving you benchmarking circuits that are just streams of Cliffords. And if you allow your compiler to do whatever it wants, it can compile those like circuits down into nothing. It can compute the outcome distribution much faster than you could probably even run it on your quantum computer. So on the other end, there are hard benchmarks where let's sample from a non-Clifford circuit, generic non-Clifford circuit. These are things like RCS, maybe you want to do chemistry. The problem with those is that verifying those circuits costs dollars, like real money. Google spent a lot of money on that RCS, like quantum supremacy paper. This is the best picture I could get of a Google data center. I like screen grabbed it from a YouTube, but it's they're enormous and expensive. So what we'd like to do is, we have access to Perlmutter. We would like to use Perlmutter as like that's sort of the scale that we want to restrict the amount of computation that we have to do for our benchmarking. I'm always amused. I was telling Paul earlier, every time I see a picture of Perlmutter, I'm reminded that I went to grad school with all those people who are on the front of it. Like, so Saul and his whole group, like that was my cohort in grad school. And it's hilarious that they're like life size on a multi-million-dollar supercomputer. So Hannah didn't even know she was on the computer. What I want to talk about today are some capability surrogates that we're using, and I'll just describe these words, that we are really like taking advantage of Perlmutter to like construct. Again, these are going to be what we consider sort of low-level program benchmarks. So we are not going to be taking advantage of the compiler. In fact, we want to exclude the compiler as much as possible because it can do very terrible things when you're trying to like understand how individual gates operate. And then your compiler says, I'm not even going to run that gate. I'm going to do something else and not tell you about it. So what we're trying to do is something we call capability learning. This is a way to formalize benchmarking where we would like to understand what is a quantum computer's capability for running a circuit. We want to learn this function, the capability function. And it is defined as, like, we call it S of C, where C is a circuit. And we'd like to say, I would love a black box that if you give me a circuit, I can tell you how well this quantum computer can run that. What sort of error? And it could be Ockel's favorite error metric. It could be fidelity, it could be trace distance, it could be how many times you have to repeat the circuit to get the right answer. Here I show an example of the total variation distance. So we have a circuit in this box in the upper left. We run it through maybe a computer that like tells us the exact answer, but we spend $1 million to do that. And then we run it through the quantum computer and we get some differences in the outcome statistics. We would like to add up all those errors and get a metric. The TVD, like Akil said, all of these metrics have different operational interpretations. The TVD can be thought of as how much of this data do I need to throw away and replace with new data so that the two distributions match. So these are some plots that we put in a paper about 5 years ago that we call volumetric benchmarks. So each one of these squares is how good is this device at running circuits that are described by their width and their depth. So we ran this on a bunch of IBM devices. We see, like, unsurprisingly, it's really good at doing very narrow, very short circuits. They're not very good at doing very wide, very deep circuits. But the capabilities of a quantum computer, what circuits it can run successfully, don't just depend on the width and the depth. They depend on structure in that circuit. And so we want this capability function to somehow capture that structure. So we're looking for some way of describing a very complicated function. And over the past 10, 20 years, we've seen that one way that we can build surrogates for complicated functions is with neural networks. Some older work that we did, like our first sort of foray into this a few years ago, was we said, well, convolutional neural networks have demonstrated a great ability to look at something and classify it and tell me what it is. So I would like a convolutional neural network that looks at a circuit trained on some quantum computer and says, yeah, this looks like something I can do, or no, I don't think I can do this. So the way this worked was we took our circuit, we encoded it we used what's called a one-hot encoding. So we built some big tensor that says each layer of that tensor is a picture of the entire circuit only showing a certain kind of gate. And then we fed that into some like a neural network, and we said, all right, we would like this to learn all the weights for these convolutional networks. We have some dense layers at the end, and we would like to predict how good are you at running this circuit. And for the kinds of circuits we were running on the kinds of devices that we were testing, they did pretty well. But they kind of ran out of steam if they got too big. We weren't able to really like match performance on large systems. So recent work, which I'm going to talk about today, is based on new kinds of neural networks that we call quantum physics aware networks. We know a lot about how errors in these systems sort of operate. And so we wanted to put a little bit of ourselves into the machine. So if we have a circuit, we can describe it as a bunch of operations, which we can label them as individual layers. We know that there's crosstalk, so we don't necessarily want to say every gate has some like special error associated with it, but we may say all of these layers have their own errors associated with them. So this is a way to capture things like crosstalk. And so this is just some math. Sorry, I hate putting math in slides, but it just says there's a unitary. It's a product of the unitaries from all the various layers, and every layer has an error operator that happens after it. So we would like to, we could also imagine taking all those errors it's just linear algebra. We propagate them all to the end. We get an error for the entire circuit. And if we can learn lambda of C, then we have a very good surrogate for understanding what is the capability of our device for running circuit C. But learning those lambdas is very hard. This is the problem of tomography. We're never going to do full process tomography on like a 100 qubit, 1000 qubit system. So what we do instead is we want to use neural networks to extract some representation of this. This is, big complicated diagram. I just grabbed it from our paper here. But again, we're using a one-hot encoding, but instead of feeding the entire neural network into, the entire circuit into one sort of monolithic CNN neural network whose job is to then make a prediction of the capability of the device for running that circuit. What we do is we feed that into a bunch of neural networks where we are trying, the output of each of those neural networks is going to be a number, which is essentially an error rate. We are trying to use these neural networks to learn error rates that we can then use a classical algorithm to make predictions of the success probability of individual circuits. So we've turned this into, instead of feed the circuit into a neural network and get our prediction, now we feed our training data into some trained neural networks. And then those give us error rates that we learn. And then we can take those error rates and do a classical computation for any circuit you give us to make predictions of the success probabilities. And this is sort of encapsulating process matrix kind of models for quantum computers that are in a way things that we can get a handle on and then use those metrics, not just to make predictions, but we can go back to our experimentalist colleagues and say, every time you run this layer of these kinds of circuits, like everything just dies. You have a serious problem with crosstalk in these gates, for instance. And this method relies on what we call error generator propagation. We can represent these circuits as we can represent process matrices as perfect process matrices followed by exponentiated Lindblad error generators. And those error generators are indexed by Pauli's. They move through Clifford circuits very easily. You don't get more of them. So if you start out with a sparse noise model, you propagate it through to the end, you still have a Pauli sparse noise model. And we just have worked out a lot of details of how to do this. And we have very fast forward simulators now built into Pigsty, which is our Python package for doing pretty much anything that we do is in Pigsty. And in my last few minutes here, I just want to flash up some results here. These are some simulated results where we are, the figures are kind of hard to read, but we know that in simulation what the actual fidelity of these circuits that we're running is, and we can make predictions. And so we plotted the fidelity of the true fidelity of the circuit along the horizontal axis, and the vertical axis is how wrong we were in our predictions. The CNNs are the old ones are these like yellow dots, and the blue dots are the new physics aware neural networks, and they do quite a bit better. But I think the important thing here is in the first, that's like we are applying these to exactly the same sort of circuits that we trained on, not the same data, but the similar sort of same kind of random circuits. Then the middle, we've trained them on random circuits, but applied them to mirror circuits. These are now, these have some structure to them that can, for instance, cancel certain kinds of errors. And we see that we do a little bit worse on these, but we still have relatively decent predictions. And then finally, we've done a simulation with 100 qubit random circuits, and we're able to make predictions here. So this is the first time we've really been able to do something that looks like tomography on 100 qubit systems. And so we then applied this to the IBM devices. And the main point here is that we have a handful of different methods, the CNNs and these like quantum physics aware neural networks. And the quantum physics aware networks are, a factor of almost 3 or so better than the CNNs that we were using before. And, we get like much better predictions of the success probabilities. So if all the dots were on the line, that'd be good. The blue ones are closer to the line than the orange ones are the green ones. So that's good. And as you can see on the right, this plot is a violin plot of the distribution of the errors. And so the blue ones are generally the smallest. That's also good. Thank you, Perlmutter. This work was made possible by lots and lots of GPUs. So, even more than the GPUs, it was made possible by like Tim Proctor, Ash Miller, and Daniel Hodem, who actually did the work. So I just get to talk about it. So if there's any questions, I'm happy to take some.